I will introduce our ICC paper named Online Clustered Codebook. In this work, we propose a novel approach to learn a visual codebook for downstream tasks, such as generation with full codebook interest utilization. This is a summary of the famous work on discrete representation. VQVE is a pioneer work that introduced the vector quantization into deep learning and applied it for the image and video generation. VQGAN is then combines the codebook learning with transformer for multiple applications. The latest mask GIT and the latent diffusion model are the excellent work to improve the generation quality using different methods for pioneer distribution estimation. VQVE is built upon an autoencoder architecture where the image is encoded into the latent representation and then decoded them back to the original image domain. The key part is the queue for the quantization operation, which looks up the closed vector from the codebook for each feature, unlike the original VE that maps the features into a fixed pi distribution, such as the Gaussian or uniform distribution. Here, the codebook is a learnable that can be optimized. However, the codebook has the collapsal issue. That means only a small subset of code vectors are used for the representation, while a large number of them simply dies off and is never updated and used. This is the real case for the VQVE trained on the CIFAR10 dataset. More than 10% code vectors are dead points, like the green points. Why does this happen? The red is feature and the green points are optimized unselected points. In the first epoch, those encoded features will look up the closed vector from the codebook and then optimize them. Those selected points will be pulled to the encoded feature distribution and will be different to the original unoptimized code vectors. In the next step, we can see the encoded feature may cover those selected points but far from the unoptimized points. Then we can only select those original selected points for the next update and optimization. Inspired by the traditional clustering algorithm, we propose to use the data points to reinitialize the code vectors. EK is the code vector and ZK head is the encoded feature. Alpha is the probability to update the code vectors. Alpha is related to the usage of the code vector. When the usage is high, the alpha will be small. Then we will just using the current code vector for the representation and update. However, the feature distribution is changed. This is quite different to the traditional clustering algorithm. To address this, we propose the running average update. That means we add the training epoch into the formula. For this online version, we will keep reinitialization the unselected points that enforce all vectors are close to the encoded feature distribution and then can be selected and optimized for all the vectors. After we adding such an online reinitialization, our method significantly improves the reconstruction performance under the same setting, and our method achieves 100% usage of all vectors. We make a deep analysis for the codebook learning. First is for the codebook size. The larger codebook naturally leads to better results in our CVQ VAE, but it is not always true for exciting vehicle approach. However, for the codebook dimensionality, there is no straightforward positive correlation between the performance and the dimension. Sometimes the small codebook dimensions yet better results than the larger ones. Therefore, we can use the no dimension vector for the representation and use them for the latent diffusion model. For the reinitialization features, we try many different sampling approaches. The offline version is sensitive to the uncode sampling methods. However, our online version is robust for random, unique, cluster, and probabilistic feature reinitialization. Therefore, we believe the average running update is the main contribution of the proposed method. We also used the codebook learning for many generation tasks like the unconditional generation on L3 dataset and also the class conditional generation on ImageNet. Thanks for your attention. More information can be found on our website and the code is released.